we ask ourselves, what is if we put ourselves at a distance r from this virtual antenna? What is the electric field radiated by this small antenna? We need this because when we have to calculate the electric field beyond an obstacle, we want to sum up all those contributions. So the question is, what is this elemental electric field due to the radiation of this elemental virtual antenna? Well, if you do all the calculations, the contribution of that elemental area is something like this. I'm not demonstrating this, so you take this for granted. And I want to comment on this equation. E0 times Vs is the intensity of the source, of the Huygens source. What does this mean? This means that the contribution due to these small elements depends on how big is the element, the area. The larger the element, the stronger the contribution. And obviously depends on the amplitude of the incident electric field. Because what is really powering those imaginary antennas is the electric field of the coming wave. Those are not real antennas. So they exist because there is an incoming electromagnetic. This is the usual 1/r dependence. So the wave generated by those small antennas are spherical waves. I draw them like this, but you can see they are spherical, so each element generates a spherical wave. And then there is a dependence on wavelength, but this is irrelevant. Now, as I said, I did not demonstrate this, but we will use this to calculate the diffracted wave. And we start with a problem that is classical. Let's imagine that we have a wall. Now I'm just designing a part of it, but imagine an infinite plane, an infinite wall, and you make a hole in it. So from the left side of the wall, there is an electromagnetic wave coming. The wall is absolutely opaque, cannot be penetrated. And our question is, if we make a hole, and this hole, the radius of this hole is A, what happens on the other side of the wall? At a given distance. In other words, we are making a diaphragm, and it is interesting to see what happens for increasing values of this force. Something unexpected happens. So if you look at this thing in a section, so this is the wall. This is the wall, and this is the radius A. The wave is coming from this side. The electric field is 0, in other words, and we are interested in calculating the electric field on the other side. Okay, let's start doing some calculations that are reasonably simple. How do we do this? Well, we imagine that on this aperture there is a distribution of Huygens sources. So we take some elemental volume, some elemental area of this aperture. We imagine that there are some sources like this, and those sources radiate towards the observer. That is, we imagine a situation like this. On our aperture there is a distribution of Huygens sources that are all radiating. And our task is to calculate the total radiation from those sources in this point. We know the contribution of each elemental source, so all we have to do is to sum up all those contributions here. We have to do a summation. That is, we have to integrate, we have to make an integral of those contributions. Before we do that, let's think about let's make some considerations. If you look at the drawing, there is. I hope you can see from here. I will bring the way. Sorry, take a while. And on this imaginary surface, we have all our imaginary sources. Now, what happens? You can easily see now, I think better than before, that contributions coming, for example, from sources that are at distance rho from the origin, contribution from those sources arrives after a path that is a little bit longer. Those points here are closer to the peak than those. So there is a phase difference between the contributions coming from those sources and the contribution coming from this source. And we have to take into account the difference. The maximum radius of the aperture, as I said, is A. So really this is the only thing we have to take into account. This small difference in path length. How do we calculate this difference? Well, if this is a circular surface, that is, this is R and this is R. difference is what I call delta with respect to the shortest path. The shortest path is arc. This one is arc plus delta. And delta can be calculated. This is a square triangle. Can be calculated simply as the square root of r squared plus rho squared. Again, since we don't want to deal with square root because those are usually nasty to handle with, we can do something we have already done. We can take r out of the root sign, and then remembering that this number here is much smaller than 1, because the hypothesis is that our point P is at a distance from the aperture that is much smaller, that it is much larger than the size of the aperture. In other words, the hypothesis for our simplification this hypothesis can be removed, but the calculation will be more complicated and it is not useful because in practice, for our applications, the obstacles will always be at great distance with respect to their size for our application. So this can be approximated as you possibly know. We did this yesterday. Sorry, I forgot one. This is this one. And we have to subtract the path difference, we have to subtract R. I forgot a bit, sorry about that. So this difference is okay. Now we put this into this equation because we can write generic distance r is this one. We can put this into this equation and we obtain the following. Sorry about that. Okay, yes. Am I going too fast? I am too fast? I have to slow down. Can you speak? Can you write again? Yeah, you have to. Yeah. Okay.
Can we have a little break of 5 minutes, please?
Sorry?
Can we have a little break of 5 minutes?
Yes, at 10:30. Is it okay? Okay. 15 minutes time. We have a break. Yeah, sure. Then in the second part of the morning, we do exercise. I just want to spend this 15 minutes with some note here, then we stop for 5 minutes. Okay. So if you put things into this equation, I just replaced capital R with small r plus delta. Now, if this is true, it is also true, this implies that R is much bigger than delta. So, as far as the amplitude is concerned, this can be approximated with R. There is no much impact on the amplitude. There is no much difference if you divide this by R plus delta or simply R, because delta is much smaller than R. But you cannot do the same simplification here, because the impact of delta in the phase term depends on the lambda. So you can do this here, but it is not allowed here. Okay, we have already seen this, but you better remember that. Okay. And now there is only some slightly tedious calculation, but it's not terrible. I give you the passages so that you may need them in the future. The total electric field is the summation, that is the integral over the aperture of the. That is, you have to sum up all the contributions all over the place. Now, this is a circular aperture. This is a diaphragm. So we naturally use a polar coordinate system where you have an angular coordinate that is phi, a distance coordinate that is, when we use rho, we have used rho there, we use rho here, and the elemental area dash is what I shadowed here. I hope it is not too small. So this is going to be the phi, and this is going to be the rho. Can you see it?
I suppose.
So please remember that in polar coordinates, ds, the area, the elemental area is rho, the rho, the phi. While you are possibly more familiar with the Cartesian coordinates where ds is dx dx. They are the same thing, but this is the elemental area in Cartesian coordinates, and this is the elemental area in polar coordinates that we use. So we want to we take our orange, they are braced, and we calculate the surface integral by integrating from 0 to 360 degrees the angular coordinate, and from 0 to A the polar coordinate. So we have I just replaced in this equation ds with its definition in polar coordinates. And we have to calculate this integral. Now, the first part is easy because there is no dependence whatsoever on FIEC. So this integration is the That was the easy part. Then we can put everything, we can take out of the integration sign everything that does not depend on rho. The only thing that depends on rho in this equation is delta. We simplify. So if you remember that this thing can be rewritten like this. Because this is a property of the exponentials, you can take out of the integral everything but this term here. And that's what we get. Now, in place of delta, we use the relation with rho that we found before, that is rho squared divided by 2r. And we have to integrate this. This is a trivial integral because it's a negative exponential and it's very, very easy to integrate. When you do that, that's what you get. Those are simple integrals. In the electromagnetic theory, there are much, much nastier integrals. So, life would be easy if we only had to. Okay, and this is the solution of the electric field beyond the obstacle. We will have to study this as a function of the aperture. We will do that later on. Just let me anticipate, as you can possibly see, that the total electric field will depend on the distance, obviously, but also on the size of the aperture. And it will depend on the size of the aperture in a way that is unexpected. Because the instinctive feeling is that the larger the aperture, the strongest the electric field on the other side. This is not true. It's completely different. But we shall see this on the next. We'll say no after the break, because after the break we start with exercises. We'll see this in the afternoon. Okay, right, for now, questions first before I right, any questions? Okay. Break and then we come back with exercises. Yes. No, no. The R is just
Oye, que me caes el roja para Jacob. Ahí. ¿Por qué me dicen que van 12 horas? Me caga. Estoy emocionado. Pero no, pues cuando ves esto estás viendo como que un poco más atrasado pero el partido. Tú solo estás viendo como que gol. Pero se lo bajó maldito, lo mejor es como tú me bajaste ayer.
Pues yo solo metí la parte más y un mortal.
Bueno, llega cámara. Pero no, ya.
Mira, yo he estado siguiendo y he visto